Hello students and welcome to chapter 5. Today we are diving into how the concepts of work, power and potential energy apply. Every move you make, every jump, lift or sprint is powered by physics. In physics, work has a very specific definition. It's not just trying hard. It's the transfer of energy when force moves something over a distance. So work is calculated using the formula force multiplied by distance multiplied by cosine of the angle between force and distance. So this angle is the angle between force and distance. Now, for example, if you lift a 10 kilogram box straight up by 1 meter, you are doing work against gravity because you're going against gravity. The force is not 10 kilogram, but rather it is the weight of the box, which is 10 times 9.8 or 98 newtons. That is the weight or the force that you are having to apply. The distance or displacement is 1 meter, and in this case the angle can be taken as 0 degrees, and therefore cosine of 0 is 1, and that's why you don't find that. So to calculate the work in this case, all you need is 98 times 1, which is 98 joules. So the unit of work or energy is joules. So in lifting the box, your muscles just transferred 98 joules of energy to the box. Next up is power. Power is how quickly work is done. So the time factor comes in. And the formula for power is work divided by time. So in the previous example, if the 98 joules of work was done in 10 seconds, then the power would be 98 divided by 10, which is 9.8 joule per second, which is also called watts. So that's the unit of power. Now, to give you another example, say that there are two runners who do the same amount of work climbing the stairs, but one does it in 5 seconds and the other in 10 seconds. Surely the faster person is more powerful. They have both used the same energy, they have both done the same amount of work, but their power is not the same. Now, this is an interesting fact that an average human can output about 100 to 200 watts of mechanical power during sustained activity. That's like powering a bright light bulb. So that's power. Third, let's look at gravitational potential energy. When you crouch before a jump, your body is storing energy in your muscles and in your position, you're crouching. Now that stored energy is the potential energy. But when you jump up, the potential energy is released from your muscles and becomes the potential energy, gravitational potential energy at the highest point. The formula for gravitational potential energy is mgh, which is mass multiplied by 9.8 meter per second squared times the height. So as an example, if a 60 kilogram person jumps 0.5 meters high, then you have m, g, and h. Multiply them and you get the gravitational potential energy of the person at the highest point as 294 joules. All right, now let's get to the problems. Number one, a person pulling a wagon holding a child pulls on the handle with a 50 Newton force. So the force applied is here along the handle and at 30 degrees. So that 30 degrees is the angle with the horizontal. The child and the wagon have a mass of 80 kilogram and the wagon is pulled a distance of 25 meter at a constant velocity. Now that is important. We'll come to that later. It's moved at a constant velocity. So you have the mass of the wagon, you have the distance moved, you also have the force applied and the angle, and it says there is friction between the wagon's tires and the pavement. Okay. Before we go to the questions, let's draw the free body diagram. From the previous chapter, you know that free body diagram means representing all the forces that act on that object. The object of interest here is not the person, but the wagon. So here on the left side, you see the forces shown. Number one, F sub A, that is the applied force, which is 50 Newton. Number two, the weight of that little red wagon. Weight is M times G. We know that. Number three, the reaction on the pavement or the pavement pushing up. That is called the normal reaction, F sub N. Number four, we do know friction is always opposite to motion. That's why friction is to the left, because the motion is to the right, as you can see here. So those are the four forces. Now let's get to the questions. What is the work done by the normal force? So that's the normal force. Remember that work is force multiplied by distance times cosine of the angle. You got to be very careful about cosine of the angle here. Which angle are we talking about? We have to talk about the angle between the force, which is the normal force, and the distance. That means the angle is 90 degrees. That's why you have to have the normal force, and then the distance is 25 and cosine 90. When you take cosine 90, you're going to get something. You check on the calculator, see what you get for cosine 90, and you will have the answer for this problem. I'm not giving it out. Okay? B, what is the work done by the gravitational force? Now look at the gravitational force. It's acting straight down. Distance is to the right. Once again, the angle is 90, and you are going to get the same answer as for A. And you will see it when you look at the value of cosine 90. Now make sure that your calculators are in the degree mode, so that you get cosine 90 degrees, not the radians, please. C, calculate the work done by the pull on the handle. Okay, now the force is the applied force, which is what? 50 newtons? Yeah, 50 newtons times D, which is 25. This time the angle is 30, because the angle between the applied force and the distance is 30. See that? Okay, so put in the numbers, you will get the answer. D, what is the work done by the force of friction? Once again, is the same formula, but now we got to know what friction is. All right, so whatever is given as F sub K is the same thing. All right, there needs to be a K here. F sub K is the force of friction. We do not know the force of friction. So we got to find it out using this idea that I told you at the beginning. If it's moving at constant velocity, That means the net force on the wagon is 0. The total force on the wagon is 0, which means if you take the x component of the applied force, it should be equal to friction. The x component of the applied force. So that's why this is the x component of the applied force, and minus friction must be 0. Why? Why minus? Because friction is opposite. It's on the negative x. So now, this is 50. Cosine 30 minus friction is 0. Now you can solve this equation to find friction. So do that first. Once you get friction, plug it in here, and then cosine of the angle. Now what's the angle? It's 180 degrees. Why is it 180 degrees? Because we're looking for the angle between friction and this, right? Oh, I forgot to put d here. It should be friction times d times cosine theta. Okay, because we need the angle between friction and distance, which is 25. Remember that?
Yeah.
So whatever you got for friction from here times 25 times cosine 180. Why is it 180? Because the angle between distance and friction is 180 degrees. So that is part D. Now E, find the total work done. You just got to add all the pieces of work you have. Whatever numbers you got, add them up, and you will get the total work done. All right, let's go to number 2. A person doing chin-ups has a mass of 75 kilogram and raises his center of gravity 0.5 meter during each chin-up. The work done in lowering the body each time doubles the amount of energy necessary. Okay, so the mass of the person is 75 kilogram. The height is 0.50 meter. And work done in this case is mgh, because the weight of the person times the height gives you work. So that means it's 75 times 9.8 times 0.5. I've given you the answer. That's 367.5 joules per chin-up. So that's for one chin-up. Now why is that important? Because part A says calculate the energy in kilocalories. We'll get to that in a minute. Used after doing 50 chin-ups. So if this is the work in one chin-up, you just multiply it with 50 and you will get the total work in joules. But don't forget that you got to double it, because that's what we calculated is only the work for lifting the body, and in lowering it, you have to double it. So that's why I've multiplied with 2. So you get your total work or total energy in joules. Now, how do you change it into kilocalories? You have to remember this conversion. 1 kilocalorie is 4,186 joules. And now you know how to change it. 36,800 joules into 1 kilocalorie by 4,186. That will give you the answer. I have not put it, but you can find it. C, what's the total power consumed in watts if the chin-ups are done in 2 minutes? Power is what? Work over time? Yeah. So the work that you get, and this time remember we need to use the work in joules. So 36,800, that's the number here, divided by T. What's T? 2.0 minutes. No. We do not use minutes in physics. So that would be 120 seconds. because each minute is 60 seconds. So what's the total power? 36,800 divided by 120 seconds, and you would get it in joules per second. What is the useful power output? I want you to look at that and try to get the answer. Well, whatever answer you get for C is the same for D. I have told you now. All right, the third question. The heart uses 7% of the human body's basal metabolic rate while resting. Skeletal muscles use 18%. And, the diagram shows you the percentage of energy that is being used by different parts of the human body even while you're resting. Okay? You're not walking, you're not jumping, you're not moving, but still for the body to maintain the temperature and all of those metabolic activities that are taking place, the body requires energy. So, what percentage of the body's energy is used by the heart and skeletal muscles? You should be able to figure that out on your own. Come on. You're given that by the heart, and you're given that by the skeletal muscles. So what's the total? All right, B part. The total energy consumption rate while resting is 1.22 kilocalories per minute. So now it says how many kilocalories per minute are required just for the heart and the skeletal muscles, okay? How much for these two? The answer, I had to give you the answer. When you add these two, you get what? 25%? That's the answer to part A. Now, 25% means 25 over 100, right? And so what you got to do is 25 over 100 times 1.22 kilocalories per minute, and you will have the answer. So all you're doing is finding 25% of this number. That's all. And then the C part, what is this in joules? We've already done this. We know that 1 kilocalorie is 4186 joules. So whatever number you get here, that's in kilocalories. You should be able to change it into joules. Thank you very much. All right, number 4. Suppose the swimmer uses mostly arm motion to pull himself along, exerting an average force of 80 Newton. That's what we're concerned. The force is given through a distance of 1.8 meter in each stroke. The swimmer does 120 strokes per minute. Wow. Okay, so each stroke, the distance moved is 1.8 meter. The force applied is given. The 120 strokes in a minute. Part A, calculate the work done in each stroke. Work is FD cosine theta. You have to remember that the force is being applied this way. The distance is also the same way. So the angle is 0 degrees between force and distance. So the angle is 0 degrees. You're given the force, you're given the distance, and then you should be able to find out the work done in joules for one stroke. So joule per stroke. Calculate the useful power. Okay, you got the work done in each stroke, but remember there are 120 strokes. And then that's in how many minutes? That is in 1 minute per minute. So now multiply the answer that you got, the number that you got here, whatever you got, put that here, joules per stroke, times 120 strokes by 60 seconds. Where did that 60 seconds come from? We may change the 1 minute into second. That'll give you the answer in joule per second because these two will cancel out. And that is also called what? Okay? That's done. So final, fifth one, that's the last one. Given that the energy consumption rate for climbing stairs is 9.8 kilocalories per minute, okay? calculate the number of kilocalories needed to climb 232 steps in 2 minutes. So now you're given 9.8 kilocalories per minute, and the information says you're taking 2 minutes. So all we need to do is do this math. The minute will cancel out with the minute, and then you will get the answer in kilocalories. B part, calculate the gain in gravitational potential energy for a 50 kilogram person if each step is 0.18 meter high. How many steps are there? 232. Each one is 0.8 meter high. So to get the total height, you multiply 0.18 with 232. Does that make sense? Once you get the height, you know the mass is 50, you know the value of G, plug that in, and you will get the gravitational potential energy in joules. And then you're asked to convert this to kilocalories, okay, which we know how to do. We've done that a couple of times before. And also you have to compare your result with the answer to part A. So you got an answer here, right? Compare that with what you get when you change it into kilocalories. And you will see that the energy in part B is smaller. Why? Actually, part C, it should be part C. Okay. It'll be smaller. I've given you a clue here because the body requires energy even when not doing anything. Remember, that's why it's called the basal metabolic rate, to keep the body warm. And for the other organs, for the heart to beat, for the kidneys to be functioning, all of this requires energy, and that is not included when we calculate MGH. That's why the energy in part A is much larger than in part C. All right, so that brings us to the end of problem set 5, and hopefully this was useful. And if you have any questions at any time, you can reach out to me and I will support you. Thank you, and see you on the next one.